microphone for the video? Oh, good, because I don't like microphones. I like to wander around. And can everybody hear me okay? No, it's not usually a problem. In fact, actually, my colleague Bob and I both have loud voices. And when we have a conversation in the hall, we're often asked to either move or have the doors shut randomly around the hall. We actually sat on opposite ends of a sofa one time at a party, and one of our other colleagues was sitting between us, and he said it took him 6 months for his hearing to get back to normal. So anyway, I don't think we'll have any problem hearing. So I'm going to talk about the implications of climate change on Nebraska, and I'm going to focus for you guys on some of the implications for water resources at the end. I think you probably all know a little bit of the history here. I'm not going to belabor this, but this report was produced in response to and maybe in spite of legislation passed by the legislature last spring. And really what we did was we did an overview of the available literature. And we were fortunate in that regard to have 2 sets of reports that had been released just at about the time we needed to do this, which in themselves were essentially reviews of the literature. And so what we did was kind of a review of the literature and boiled it down from the global or national perspective that these various reports were focused on to something that was more appropriate to the level of an individual state without doing a lot of, or really any new research for Nebraska. That doesn't mean that we aren't involved in doing research for Nebraska, and we do have some things that we can share. I don't have a lot of that. In fact, I think I eliminated the one slide that I did have because it was something I really didn't want to spend a lot of time explaining. So anyway, so these are the 3 working groups from the Intergovernmental Panel on Climate Change from their 5th assessment report that came out. This one came out last September, and these 2 came out in the spring on the physical basis of the climate change, adaptation, impacts and adaptations, and then mitigation. We really focused on these 2. And then this past spring, I think it was in May, the 3rd National Climate Assessment, a report that's authorized by Congress, was released. And so this obviously focuses on a more national scale for the U.S., and it also has broken down into regions, one of which is the Great Plains, which, as you know, is a very varied region going from Texas to North Dakota, but we were able to glean some things out of there that were a little bit more appropriate for Nebraska. And then we also asked colleagues and stakeholders around the state to write short kind of vignettes about their interpretation of mainly this report and the impacts that it would have on either their sector of the economy or a specific region. So that's all in that report. And copies of the report are available. No, they're not for sale. You can also download it as a PDF if you haven't already. So I'm going to talk a little bit about the science of climate change, and then talk about some of the observations of how the climate has been changing, and then finish up with some projections of climate change for the remainder of the century, and then, like I said, talk a little bit about water resources, probably a little much less than you'd like, but I'll be glad to answer questions if I can. So basically, I want to start out with something that we always have to make a distinction between, is the difference between weather and climate. Okay, weather is what's happening right now. In fact, meteorologists think of weather as when there is actually something happening. Okay, so when it's a clear sunny day, there's no weather. Okay, as far as we're concerned, we want something to be happening. That's weather. Okay, but it's the state of the atmosphere. It's the temperature outside right now, the relative humidity, whether it's cloudy or clear, or the wind, how strong the wind is, and so forth. Climate doesn't exist in reality. Okay, there is no climate except what we do. Okay, what we make up. We take the weather observations that we make over some period of time and take averages and look at the variability, look at extremes, look at frequencies of various things occurring. That's climate. It's a human construct. Okay, it doesn't exist in nature without humans doing something. Okay, or as what's been attributed to Mark Twain, climate is what you expect, weather is what you get. Okay, Or to put it in another way, and this is something that Martha Schulsky, the director of the High Plains Regional Climate Center here at UNL, likes to say, is that climate is the clothes in your closet. Okay? Weather is what you put on that day. Okay? So you know you're going to need a winter coat in Nebraska. You know you're going to need some t-shirts and shorts in the summertime, right? So you have all that stuff in your closet. What you choose to wear that day is basically why you look out, what's the weather like today, and that's what you're going to wear. Of course, sometimes in Nebraska, you may need a winter coat in the morning and shorts in the afternoon, so it's kind of hard. But that's another way of thinking about it. Okay? And there's difficulties in doing projections of the weather. We know that weather forecasts sometimes are wrong. And climate is a different problem to predict, but actually I'll say it's somewhat easier in a lot of ways. So, the problem for climate change that we're going to talk about today is what are humans doing, okay? And so I'm going to start off with a very, what looks like a complicated diagram, but I'm going to tell you it's really not that hard. This is the energy coming in from the sun, okay? Hits the top of the atmosphere, that's the TOA there, top of the atmosphere. It's 340 watts per meter square. That's 340 joules per square meter per second. So every second of every day, there's 340 joules hitting every square meter at the top of the atmosphere. Well, that's average. Obviously, the sun's only shining on half of the atmosphere, so it's average over the dark side as well. Okay? That energy, that's like having a 340 watt light bulb above basically a 1 yard square area. Okay? Okay, that comes in, some of it gets reflected back out to space. That's not going to heat up the atmosphere or the Earth at all. Some of it gets absorbed by the atmosphere, some of it gets absorbed down at the surface. Roughly about half at the surface, about 20% in the atmosphere, but that's what's going to heat up the whole climate system. Okay? In order for the Earth to be in balance, we have to be emitting about that same amount of difference back out to space. So 340 minus 100 is 240, 239 going out. Okay? So we're roughly in balance with space. You'll notice there's a little bit of an imbalance, and right now, this is current today, what's happening. This is the imbalance that's causing heat to build up in the environment and the temperatures globally to go up. Okay? So why is that happening? Well, we used to always teach students that these things would be in balance and things would be hunky-dory and the climate wouldn't change. Okay, that's what we would say. But it turns out that humans have been adding greenhouse gases, and it's this side of the diagram that's getting changed. Okay, these orange numbers over here. Notice this is the greenhouse effect, which is a good thing. If we didn't have the greenhouse effect, the global temperature of the Earth would be about minus 15 degrees C. As it is, it's about 15 degrees C. So it's about a 30 degrees C or almost a 60 degree Fahrenheit difference between what would happen if the Earth didn't have a greenhouse effect and what it had. So it's a good thing in that regard. What's changing is that we're making the greenhouse effect stronger. Okay, so this is the greenhouse effect. If you notice, the numbers over here are bigger than what's coming in from space. So this is a really important thing that's going on over here that changes our climate from about minus 15 to about 15 degrees on a global average. But what happens is everything, as it absorbs energy, it heats up. As it heats up, it emits what we call infrared radiation, long-wave radiation, at the temperatures that we see on Earth. That means the walls of the room, the floor, the ceiling, you, me, the tables, the air in the room are all emitting long-wave radiation. Now, we don't notice it because we're all at about the same temperature, so we're all emitting equally to each other. So you don't like feel heat coming off from the person next to you or something like that because you're just emitting as much back to them. So it doesn't, you don't notice the difference. You do notice it like when you turn on your electric burner and you don't see anything happening right away, but you can feel heat coming off of it, right? That's infrared heat coming off of it. And then after a while, after it heats up more and more, it actually starts to get hot enough that the energy that's giving off starts to become part of the visible spectrum. We see the coils on the stove glowing orange, and if they keep on going, maybe red, and then eventually, if you really had a really amazing burner, it might glow white. Okay, as it gave off more and more visible radiation. And so you see that. Okay, so this is the greenhouse effect, and what happens is as you add more and more greenhouse gases into the atmosphere, more of the energy that's emitted by the surface gets absorbed by the lowest part of the atmosphere and then is radiated back down to the surface. Now we still, the whole system isn't going to get too far out of whack, because what's going to happen as this happens is, if the atmosphere is absorbing more energy, it's going to heat up, and so it's going to be able to emit more radiation back out to space. So eventually you're still going to have something close to a balance, okay? But what's cycling back and forth between the surface and the lowest atmosphere, and then the lowest atmosphere is radiating back down to the surface, is going to get more and more, which is going to raise the temperature down in the lower part of the atmosphere. So that enhanced greenhouse effect is the thing that's working. Now this is not new science, right? This is something that we've known for almost 150 years now, okay? Well, almost 200 years now. Back in the early part of the 19th century, we realized that carbon dioxide absorbed infrared radiation and not sunlight. Back in the early part of the 20th century were some of the earliest calculations of the greenhouse effect, and they weren't far off, okay, about how responsive the system would be to it. They were crude, but they were actually pretty much. So not new science. Okay? We've known this for a long time. Okay, before I go on, I have to do some definitions too, because although I won't use them too much here, you may read them if you look at the report. You need to make the distinction between a forcing, okay, and a feedback. And this gets a little confusing sometimes when we're talking about climate processes. So forcing is something that's external. It's a push on the system, okay? So you push the system, and the system is going to respond. And the system in this case is the climate, okay? So these kinds of forcings can be natural, okay? The amount of sunlight coming in could change. Volcanoes which aren't part of the climate system themselves can change what's in the atmosphere, and those can have an impact on the climate system. Or they can be human-caused or anthropogenic, things like these greenhouse gas emissions, where we're putting more CO2 into the atmosphere, primarily through fossil fuel use, and also things like land use changes. If you cut down a forest and put in an agricultural operation, it changes the reflection of the surface. Forests tend to absorb a lot of sunlight. Bare fields tend to reflect more. So those kinds of things can change how the climate system responds. Okay? It's going to have a response. Once the climate system starts to respond, there are certain feedbacks involved, inherent in the system, that are internal to the system itself. Okay? And these feedbacks can be either positive, which would amplify the initial forcing, okay, or they can be negative, which would damp the initial forcing back toward its original state. So, I think we all have familiarity with the positive feedback. That's the squeal when you get the microphone too close to the speaker, and it starts, any little noise gets amplified rapidly, and it makes that squealing noise. Okay? And negative feedback's a little harder to work, but it's basically kind of like brakes. Okay, it's just you push harder, and it gets more resistance against it, and it works to restore the system back to its original, or toward its original state. Now, the thing that makes the climate system even more difficult is some things can be a forcing in one context and a feedback in another. And CO2, one of the major greenhouse gases, is one of these things. When we add CO2 to the atmosphere due to fossil fuel burning, it wasn't going to get there naturally. It was something that we're doing separately. And so that's a forcing. Okay? On the other hand, if you look back in Earth's history, you'll notice that there have been times as the Earth responds to changes in solar radiation due to the orbit and various things, the Earth would start to warm up. As the Earth warms up, the oceans warm up, it releases CO2. It can actually amplify that initial warming, because then that release of CO2 is a natural response of the climate system, and so it's a feedback. And it's, in this case, it can be considered a positive. So sometimes it's a forcing, sometimes it's a feedback. In our case, what we're talking about is a forcing as we add more greenhouse gases into the atmosphere. Okay? So the Earth is warm. Okay? There's really very little resistance to that anymore. It is getting warmer. The temperatures near the surface are going up. The amount of water vapor is going up. This is important because as you increase the temperature, the atmosphere can hold more moisture. That means there's more moisture in the atmosphere, and we'll see later, when it rains, it's possible to rain harder because of that additional water vapor. Sea surface temperatures are going up. Ocean heat content is going up, and this is actually one big thing that's very important, because a lot of the heat that's being trapped by the system is actually being stored in the ocean, and ocean temperatures are going up, but rather slowly, because water can absorb a lot of energy without changing its temperature, unlike the atmosphere itself. When you add a little bit of energy and the temperature goes up. Glaciers and ice sheets going down, snow cover going down, sea ice has been going down, especially in the Arctic. Dramatic changes in what we call the cryosphere around the whole world. Okay, and so you can do this now, and these are the same 10 things, showing them in the actual data numbers. Land surface air temperature going up, sea surface temperature going up, air temperatures over the ocean going up, sea level going up as the oceans expand because they're getting warmer, and also as those ice sheets and snow cover on land melt and the water flows into the ocean. Temperature in the lower part of the atmosphere going up, heat content in the ocean going up, specific humidity, a measure of the amount of moisture in the air going up, northern hemisphere snow cover going down, glacier mass balance going down, and the sea ice in the Arctic decreasing quite dramatically over the last 50 years or so. Okay, so here's our global average temperature from 1880 to 2012, essentially. The reason we only go back to 1880, this is based on instrumental data, actual observations, and we can go back to 1880 because that's when we have a fairly widespread record of global temperatures. Prior to that, we didn't have a lot of stations, and we still don't have as many as we'd like. In the southern hemisphere, we didn't have, there were a lot of places that were unrepresented. But basically, once you get that back to about 1880 or so, you can start to have a fairly good, robust statistical measure of the global average temperature. Okay? And I think there could be a little debate that the average temperatures now are higher and that the temperatures have been going up over the last, say, 100 years or so. Okay? Naysayers will point out that, hey, it's not changing anymore. Well, hey, it wasn't changing there. Hey, it wasn't changing very much there. There's times when it stops for a little while, then it starts up again, okay? That's the natural variability in the climate system. But nobody's gonna argue that it's not warmer in the latter part of the 20th century and the 21st century than it was back in the early part of the 20th century, okay? That's a big difference. It doesn't look like much. We're talking about temperatures now, this is based on an average over the 1950s to the 80s, that period there. And so the temperatures are about 0.4 of a degree Celsius less and about almost 0.6 of a Celsius more, so almost a 1 degree Celsius difference over that 100-year period. It doesn't sound like much, okay? But keep in mind that when we go to a glacial period, the global temperatures were only 4 or 5 degrees Celsius cooler than they are now. Okay, so this is already a quarter to a fifth to a quarter of that kind of change. So it's a pretty big change, and it's happened over 100 years, not over thousands of years. So it's happening at a very rapid rate. In the United States, temperatures have generally been going up. These are trends over the period from, again, about the early part of the 20th century up until the present. And you can see everything, except for a little bit down here, is red. Okay, to some degree or another, the changes have been positive over that period of time. The exception is in some areas of the southeast, and that's really driven by the 60s, basically the 60s and the 70s. Those 2 decades were really quite a bit cooler in those areas than it had been earlier or is now. And the reason for that mainly is the fact that the TVA, instead of building a lot of dams like they were originally envisioned to do, built a lot of coal-fired power plants that put a lot of sulfates into the air. Those sulfates become little aerosol droplets that are fairly long-lived, and they reflect a lot of sunlight. And so we think that was probably one of the largest reasons for the cooling. And then with the implementation of the Clean Air Act, and they started cleaning up those things, those aerosols started to decrease, and now we're seeing that the temperatures now are on the positive side, even in that region. You know, almost everywhere is experiencing an increase. Some places, especially in the Intermountain West, extreme increase in also doing. Jerry Meal at the National Center for Atmospheric Research started looking at temperature records. And if the climate's not changing, and you would expect that you would set as many high temperature records as you would low temperature records around the country in a given year, right? That would make sense. If the climate's staying the same, you'll set a few records on the high end and you'll set a few record low temperatures. What he found was that was what was happening back in the early part of the record here. In fact, actually it went down a little bit, more cold records. Actually, it turns out that that's largely because of that cooling in the southeast. And then what's been happening since that time is a steady increase, and now we're setting twice as many record high temperatures as we are record low temperatures. Okay? So what's happening is the distribution is gradually shifting. The temperature distribution is gradually getting warmer, and so there's more of those extremes out in. It's easier to set a high temperature record than a low temperature record. Yeah, twice as many highs as low. Okay? Changes in the frost-free season. Okay, if you have from the earliest frost in the fall to the latest frost in the spring to the earliest frost in the fall has been increasing. And this is over, I believe, since about the 1950s. I have to go back and check for sure. Basically, in our part of the world, over a week longer now for a frost-free season than before. In the Southwest, 3 weeks longer. Okay, that's pretty amazing. That has an impact. It might sound good. Oh, great! We can, have a longer growing season. We can grow more stuff. But what does that stuff that we grow use? Water. You need more water then to have that longer growing season. So, and the peak of the growing season may also be getting hotter. So, okay, now we got some issues. Okay. What about precipitation? This is a tougher nut to crack. What we're seeing is that in large parts of the country, we're actually seeing increases in precipitation over the same time period from before. So here's our part. We're seeing more positives than negatives. In the southern Great Plains, same kind of a shift. Out in the Southwest, there's an indication of less precipitation. Basically, one of the ways that we interpret this, and this is also matches up with the global perspective on precipitation, is that dry areas are likely to get drier and wet areas are likely to get wetter. Now here in Nebraska, we're not really a dry area or a wet area, we're kind of in between, and that's actually kind of what we find is that we have some parts of Nebraska that have been, these are observed, okay, up until the beginning of the 21st century here, wetter in the eastern part, drier in the western part to some extent. And part of this is because, as I said earlier, as the climate gets warmer, as the atmosphere gets warmer, it can hold more moisture. What happens then when it rains, because you get heavier rains, okay? And that's actually been observed as well. Changes in very heavy precipitation has been increasing. So these increases in precipitation that we're seeing are largely in heavy rainfalls, okay? High events, okay? Which is not a good thing because a lot of that rain can't then infiltrate, it runs off, okay? And that may not be a good thing. It could lead to enhanced flooding, okay? And when you have heavier rain and it kind of depletes the atmosphere of moisture, it takes a while to build back up again to get another rainstorm. And you can actually have longer time periods between rain events. So you may have more consecutive dry days than you do now. That's another thing that we think is happening in a lot of areas. Okay? So that's the science kind of behind it in a nutshell. That's the observations we've been seeing that show that in fact it is happening. How do we know it's humans that's the cause of this? Well, there's some good evidence. I'm only going to outline a few of them here. The surface temperature has been going up. We saw that for the last 100 years for the globe and also for most regions of the world. And this is the same time that humans are putting more greenhouse gases into the atmosphere. Okay, so if we look at for example, the CO2 concentration from the 1880s up until essentially the present here, and plotted alongside the temperatures, we see that there's a pretty good correspondence between those two. Okay, now that's not proof. It's just we can plot these things on the same graph, but the correspondence between those two is pretty good, and the science says that in fact it is a cause and effect relationship. Okay, the basic physics that I said we established back in the 19th century, and the more detailed calculations that we started doing starting in the 20th century shows that we add more greenhouse gases, the temperatures at the surface and the lower part of the atmosphere should increase, and that's what we're seeing. Okay, and so we can actually break out. Here's again the same temperature record we saw before with a few extra lines on it. But these are several different records, again, that same time period. And we can start looking at what are some of the things that might cause temperature changes? Well, the El Nino, we know, has big global effects. And we plot our estimates of what the El Nino effect on global temperature is. And really, I don't see a trend. A lot of variability when El Nino happens, it changes things quite dramatically, but there's no trend there. Volcanoes, no trend. You can tell when there's a volcano, a big volcano, because the temperatures go down. So it's not even going in the right direction. You put up more stuff into the atmosphere, it reflects more sunlight. The Earth cools for a year or two after a big volcanic eruption, and then it goes back up to where it was, but no trend there. Solar, no real trend. Excuse me, in solar there's some variability. There's a well-known 22-year cycle in solar variability, and it goes up and it goes down, but no real trend. Other things, this is the Atlantic multi-decadal oscillation, a bunch of other things that we know, kind of like El Nino and the Southern Oscillation. These are some other ones, and we put them. We try to figure out what their impact would be. And again, there's ups and downs, but basically no trend. Okay. Why sort of blank? Well, when we throw in the anthropogenic causes of greenhouse gases going up, clearly there's a trend. Okay, this is the forcing that we can ascribe to that additional CO2 in the atmosphere. It's the only thing that we can figure out that has this strong trend over the last 50 years or so. There was a smaller trend in the earlier part of the record, but we weren't using up fossil fuels at quite the same rate as we are today. Now, I said that the surface and the lower atmosphere should be warming. It also, we find that the stratosphere, the next layer up in the atmosphere, above about say 12 to 15 kilometers up to about 80 kilometers or so, has been. We would expect, if the greenhouse effect is the cause, that area would be cooling. If it was solar variability, the whole atmosphere should be warming up. Okay, so we can look at that. The lower stratosphere has been cooling. This is a shorter time record because it's basically based on satellite measurements and some balloon launches, but mostly satellites. We didn't have enough balloon launches prior to about 1960, the late 50s, the International Geophysical Year 7, I believe. We started launching more balloons, and so we have better temperature records and then satellites. The lower troposphere, down where we live, warming, the stratosphere cooling, consistent with an increase in greenhouse gases and being the cause of the warming. Okay. And finally, detailed simulations with climate models, okay, are only able to reproduce the observed warming when we include greenhouse gases. So here's some measurements. These are the models that were run for the last IPCC assessment back in 2007. These, the red and yellowish lines here, are from the most recent report that was just released this last year, and then we have the observations. Okay, so these are historical runs going back again to the early part of the record, and we can see that the models, the red line and the blue line are the models. It's hard to see the blue line because it's underneath the red line most of the time, and the observations do match fairly well. Okay, the grayish, bluish gray, and the mustard color kind of thing are the individual models, and you can see the individual models. A lot of variability in them, but when you average them out, they match up with the observations pretty well. If we take a look at the observed trend over the last 60 years of these the last 60 years of the observations, and compare it to the average trends in the models, it also matches up with the pretty well with the geographic variation. Areas where there's little change match up fairly well. The amplification that we find in the polar regions matches up very well. The highest temperature increases tend to be where we're melting a lot of snow and ice and exposing dark ground that's then absorbing more sunlight and then heating up even more. So we get a lot of polar amplification when we include when we run these models. Now, the nice thing about models is you can turn things on and off. You can say, oh, well, just ignore the CO2. Okay, we're just not going to let CO2 go up. What would happen? And if you run the same models and you turn off the increase in CO2 that took place over this time period, and remember, the CO2 emissions and the concentration really ramped up after after World War II, basically. You notice that the observations go that way, and the models stay basically flat. There's some downturns here where we do include volcanoes, so where there were volcanoes, there were sharp downturns, but they came back up again. But basically, very little change over this time period if you don't include those greenhouse gases. And so if we only look at natural forcing, okay, it turns out that actually most of the world would have experienced a cooling trend over that time period because of reductions in the amount of sunlight coming. All right, so we only have one Earth. I mean, most, the gold standard of science is to have a controlled experiment, and a control and experiment. We only have one Earth. We don't have a lab where we can stick the Earth in a Bunsen burner, over a Bunsen burner in a beaker and heat it up. So we can't do that. So we have to rely on numerical models to project then what happens in the forcing. Now, I hope I show you that these climate models do a reasonable job, okay? They're not trying to predict what the weather's going to be like on your birthday in 20 years or anything like that, okay? They're not going to try to do that, but they're going to try to predict what the climate statistics will be like in the future, okay? And it's a lot easier to actually project a mean out than it is to get the exact details on a given day or a given year out in the future, okay? This is kind of like if you were to stand outside Memorial Stadium on a Saturday in the fall and say, I bet the average, if you do a little bit about average people in Nebraska, you could probably predict the average height or the average weight of the next 30 people coming out of the stadium fairly well. But I dare you to predict, without seeing them, the average height or weight of the next person coming out. And it's probably not going to be very likely that the next person coming out of the stadium will exactly match your prediction. But the average, knowing a little bit about humans, you can probably predict with some greater confidence. Okay? So we can do the same kind of thing with the climate system. We can run the models out. We can take a bunch of different models, average all the results together, and the averages tend to match up with the observations as we saw in the past, and they're our best bet of projecting what's going to happen in the future. Now, these models are very complicated and very comprehensive. Okay, they're basically a group of models that are joined at the hip, okay, and pass information back and forth. There's a general circulation model of the atmosphere, a general circulation model of the oceans. So we're studying how the flow of the atmosphere, the flow of the ocean takes place, how they transport heat around the world. We have land models that predict how much energy is going to go into evaporating water and how much is going to go into heating up the air. We have sea ice models, and we have all sorts of different models, and they're joined together and respond to changes in the incoming solar radiation and changes in the atmospheric composition. So we can do that, and they actually do, like we saw, pretty well. And these models are increasing in complexity and increasing in spatial resolution all the time. Okay? So I'm going to give a real quick some projections of future climates. Okay. First, I'm going to start kind of with the big picture, kind of the global average, like we've been looking at, and then boil down to some global geographic distributions, and then regional, more on the U.S. Scale or North America, and then try to say some things about local changes. Okay. So if we do again. Look at average global temperature projections over the next, well, till the end of the century here. These are various scenarios that we've run over the past. The dashed lines here represent ones from the previous IPCC assessment. The solid ones are from the more recent one. And these are the averages for various scenarios that are saying basically how humans are going to change the atmosphere over time. So we can have kind of the rosy picture down here that we all get together and say we're not going to emit any more CO2. It's going to the climate system will stabilize at about a 3-degree Fahrenheit temperature increase. Okay. Like I said, it's kind of a rosy picture. I don't think we're going to see that anytime soon. That we all get together and stop burning fossil fuels. On the other hand, the red line here represents what we like to call, it's actually officially called RCP 8.5, which is not very exciting. It's basically the business as usual scenario. We keep emitting and increasing our emissions of greenhouse gases for the foreseeable future. And then we're looking at something on the order of about an 8.5 degree Fahrenheit temperature increase. But by the end of the century, very large. Remember, this then is on the same order, 8.5 degrees Fahrenheit is about that 4 or 5 degree Celsius change in the opposite direction to get us into an ice age. We're looking at a change as large as going into a global ice age, but in the opposite direction. Turns out that obviously we saw that those models had lots of variation, and the variation of all the models might be something like I'm doing here, there and there. So at the low end, it might be closer to 2 degrees, it might be closer to 4 degrees. Up here, it might be closer to 7 or 7.5, and it might be as high as up to 10, according to the individual models. Okay. But what I want to say is the individual models have a range like that. Our scenarios have a range like that. Okay? The biggest uncertainty, and while we know these models, there's some uncertainty in the model projections, the bigger uncertainty comes from which scenario, which path humanity is going to follow. And I can tell you, projecting out climate change is a tough nut. Okay? But you try projecting what humans are going to do over the remainder of the century. Okay? That's way harder. Okay. So, what does it look like over the globe? This is, again, that low-end scenario, the rosy picture. This is the high-end scenario. And we can see again, everywhere, I don't see any of these blue areas over here. Everything's in this yellow to red and almost black here. Most of the models are in agreement almost everywhere for all of these. And again, we can see things like that polar amplification in all the scenarios. So again, some warming at the low end emission scenario, very significant warmings. The warmings are higher over land areas than over the oceans, higher in the polar regions than in the tropics, but again, increases everywhere. Boil coming down now to something closer to our area, central North America. This is wintertime projections, and again, you can see the variations in the various models here, and the different colors and the different scenarios, and you can see the averages for the low-end scenario. These are in Celsius now instead of Fahrenheit. You can tell the difference between the IPCC graphs and the National Climate Assessment graphs. The IPCC is like most of the world uses Celsius, and the National Climate Assessment is Fahrenheit for us Americans. And so basically, you can see again about a 1.5 to 2 degree temperature increase at that low end to somewhere around a 5 or 6 degree increase for the higher end. So it's actually kind of mirroring the global average annual temperatures pretty much for the wintertime in the central part of North America. These little diagrams out here show the temperature range for each of those scenarios, so the low end to the high end scenarios. These are traditional what we call box and whiskers diagrams. So the bar in the middle is the median change. The top and the bottom are the lower and upper quartile. So 50% of the models fall in that range, and then these two represent the extremes of the distribution. So you can get an idea, but all of the scenarios are showing a warming in the wintertime. And this kind of goes along with that polar amplification. Cold temperatures are in areas where it's cold, increase more rapidly. Times of the year increase more rapidly. In the summertime, again, though, we still see for our region, because we tend to be fairly dry in the summertime, large increases in temperature as well. In areas where it's moister, you don't see as much of a temperature rise. But again, we're looking at it as somewhere on the order of that about 5 or 6 degree temperature change for the average at the end of the century. At the low end, maybe only a couple degrees Celsius, but still an increase. Precipitation, not real big changes when we look at these. This is now the cool season from October to March. Very small trends. The low-end scenario shows almost no change, and the high-end scenario shows a fairly large change, maybe about 10 or 15%. Okay. Well, you guys, how much does it rain in the wintertime here? How much water do we get in the wintertime from October to March? If it goes up by 10%, is it a big deal? It's a help, but it's not a big deal, right? You go from 5 or 6 inches to 5.5 inches. It's just 6.5 inches. You get an extra half an inch of water. Summertime, the changes are minuscule. Okay, we're looking at all the projections by the end of the century are somewhere on the order of of increase in that region. Of course, a lot of variability among the models. Okay? Precipitation is one thing that the models are weaker on, and I could go on and tell you some reasons for that in terms of the physics, but that's been a long time for that. Okay? Nebraska. Okay? Boiling it down to Nebraska, this is stuff we gleaned out of mostly the National Climate Assessment, but also our own, some of our own work. Temperature increases in the range of 4 to 5 degrees C to 8 to 9 degrees Fahrenheit, 4 to 5 degrees Fahrenheit to 8 to 9 degrees Fahrenheit, and these are based on the kind of those two end members of the emission scenarios. And that is, so the 4.5 to 8.5 degree, that difference kind of is due to those uncertainties in what humans are going to do over this next 80 years or so. A lot of days, a lot more days over 100 degree Fahrenheit, increasing in the low end scenario by about 2 weeks. 2 weeks worth of more days in over 100 degrees to more than 3 weeks in the high end scenario. So a lot more days where the temperatures exceed 100 degrees, which is obviously stressful for livestock, plants, and us. Me especially. I don't like hot weather. Number of warm nights are expected to increase. We're not going to have as many low cool nights. The frost-free season will continue to increase. We saw that over the last 50 years or so, it's gone up by about 9 days in our area, an additional 2 weeks of frost-free season by the end of the century. So here's those various emission scenarios. Now we can actually pick out Nebraska on the maps. We see that it might be on the order of, again, that 4 or 5 degree, 3 to 5 degree range in there, and then here maybe that 8 or 9 degree range for our area by the end of the century. Okay. What about precipitation? Again, highly uncertain. Little change in the annual totals for the low end scenarios to slight continuing increases in the higher end scenarios. The percentages changes tend to be larger in the winter and spring, smaller in the summer and fall. The summer in a lot of the models is projected to actually have less rainfall in the future, okay, in some of the scenarios. Heavy precipitation events are expected to increase. Again, we're adding more moisture to the air, it rains out in heavier precipitation events. Okay. When you start combining the changes in temperature and the changes in precipitation that we might get, the changes in soil moisture over our area show a decrease of 1 to 5% for the low end scenarios, to 5 to 10% for the higher emission scenarios. And I believe, I have to go back and check this, but I believe this is during the growing season, or the beginning of the growing season. Okay. So those are significant. Okay. So again, we can see this is the low end scenario, the rosy picture, or what they decided to call the rapid emissions reduction scenario, or the continued emissions scenario, the high end scenario. We can divide it up into the different seasons of the year. Again, these are percentage changes. So even though we see big green blob over Nebraska in the wintertime, we're going from a couple inches to a couple inches plus a couple tenths. So not a huge increase. Another thing that we need to look at if we're interested in water resources is what's happening over the Rockies. Are we going to get more precipitation in the Rockies? Maybe, but the problem is that it may be a switch from snow to rain. We want snow to accumulate in the Rockies to be the water supply in the following summer for our region and for the Southwest. But if it rains, that water comes down the system and out to the Missouri pretty quick. So it doesn't help as much. Anyway, in the summertime, again, as we said, in the high end scenario, remember that here we're not showing any real change. Basically the white areas the models were in such bad disagreement they didn't plot anything, and so we have no consensus in the low end scenarios, but in the higher end scenarios, the models pretty much agree that Nebraska will have a decrease in precipitation over that time. So maybe an increase in the spring, a lot more heavy rain events in the spring. These are associated with, these are multipliers for heavy precipitation events, and we're expecting somewhere on the order of twice as many heavy rain events in the future. In the high end scenario, maybe a slight increase in the maybe 1.5 times more rain events, heavy rain events at the lower end. Soil moisture, as I said, envisioned to decrease. Here's Nebraska, somewhere right about there. And it shows a decrease in near surface soil moisture in the latter part of the century. All right, so in the National Climate Assessment, and I don't expect you to read this, okay? The National Climate Assessment did different chapters, different sections on various sectors of the economy or various impact areas. And this is they came out with key messages for each chapter at the end. And these were the key messages that they wrote up for water resources across the United States. And so I looked through there's 11 of them, and I said, oh, that's too many. I'm talking to people who are dealing with water, and we got to concentrate. And so I cross out the one that doesn't affect Nebraska. Now it's 10. Okay? So this is something you guys want to worry about. But that's way too much as well. So a couple of pictures. Water quality, one issue. Water quantity. So what the people who were writing this chapter came up with an idea of, okay, what's the risk index of having a sustainable quality water supply? And they said, okay, well, what counties in the U.S. have an extreme or a high risk? And well, they plotted all of them, but in terms of by the middle of the century, this is the middle of the century with no climate change effects. It looks like somewhere on the order of around 300 out of the something like I forget what it is, over 3,000 counties were at risk, about 10%. If we start to incorporate the climate change effects, it turns out that the high and extreme risk counties, it's about 1,000 or so out of the. So we go from about a tenth to about a third of the counties are going to have a difficult time sustaining a quality water supply as climate changes. So the climate change impacts, the other risks are due to pollution and population growth and things like that. When you include climate change effect, you can see much of the country starts to have significant sustainability problems in terms of water supply. And of course, the other message that I think is really in these various assessments is that we expect to see increasing variability as climate changes. Okay? That the variability goes up. So kind of paradoxically, in an area like Nebraska, we could end up with more flooding and more drought at the same time. Why? Well, you get these heavy rain events that leads to more flooding, and then you have more time between rain events, perhaps that can lead to drought. And so we can end up with both things, and of course across the state the size of Nebraska, we could have both things happening at the same time. If we have anything to look at, again, the same 10 messages out of here now. Two that I blew up so we could all read them. Really talk about what you are involved in more. That water resource managers and planners are going to encounter new risks, new vulnerabilities, and new opportunities. Okay, but you might have to think about changing some of the existing practices in terms of managing. We need to increase resilience and enhance our capacity to adapt to strengthen these. And there's obviously a lot of barriers, and many political barriers I'm not going to talk about. I'll let you guys hash those out. Are going to present some challenges to implementing various strategies. So, just to summarize and leave a little time for questions here. Climate is changing. It's observable. Over the last 50 years, we can say the IPCC does say with near certainty that it's due to human activities, due to the burning of fossil fuels primarily, with more greenhouse gases in the atmosphere. We've seen some increases in extreme weather and climate events that have been taking place in the recent decades, and more of the increase in these events is starting to be able to be attributed to these human activities in terms of greenhouse gases. The reliability of water supplies, as we showed in terms of the sustainability risk, is probably going to be reduced as the climate changes. Even where precipitation is going to increase, the seasonal distribution and the number of extreme events may change in adverse ways. Increased evapotranspiration due to the higher temperatures will probably more than offset any increases in precipitation, and probably lead to decreases in soil moisture in many areas of the world, including, we think, in our area. And finally, the impacts that are related to climate change, maybe not so in places like the United States where we have the capacity to adapt, but the impacts really are evident around the world, and they're expected to increase through the remainder of the century. And I always like to add and beyond, because a lot of these graphs stop at the end of the century here, but those changes keep on going. Right? So we have to keep that. So I leave you with that.